Well, why don't we start, and a few stragglers will come in, but I wanted to start with something completely different anyway. First, I just want to say, welcome to York, and hopefully tonight we can all learn something. What I'm going to do is talk about the science in the movie Angels and Demons, and then I really would like to open it up and have questions. The idea is that there was Sony Pictures and Cern, the laboratory in Geneva, got together and decided that it was in their mutual interest to promote each other. And so they set up a series of lectures across North America, of which this is one. There's about 30 of them all over North America, all over the United States and Canada. And the idea is that since the fundamental idea in the movie has to do with a physics of antimatter, which seems fairly exotic to people, the idea was to use that as a platform to try and describe what antimatter is. So that's what I'm going to try and do for you this evening. And so what I want to do is show a little bit about CERN and the LHC, the Large Hadron Collider, try and describe briefly what this God particle is that they're talking about. And then mostly I want to talk about antimatter, talking about the production of it, the holding of it, and then also I'll finish off talking about the moment of creation. So CERN is the European Laboratory for Particle Physics. It's a French acronym, Conseil Européen pour la Recherche Nucléaire. You can see it here on the right. You can see the Geneva airport. You can see Lac Léman, Lake Geneva up top. And of course, the white line is the accelerator. There is no such white line. Of course, it's been put on this photo, so you could see it. It was founded more than half a century ago, and more than 9,000 scientists have done research there, including a lot of Canadians. So, who's seen the movie, by the way? Oh, a fair number of people. Okay. So this is what CERN, the control room, looks like in the movie. Okay. And this is what CERN control room really looks like. It's fairly more modest and not quite so full of glass. This is Ron Howard directing particle physicists to look like particle physicists, and you notice that they're in particular wearing white lab coats. So I wore one this evening for your honor. But in fact, these are what physicists really look like. So I'm going to take this off because they don't wear those. And that's actually Ron Howard visiting the site of the experiment that I work on at CERN. And that's some of my collaborators. I collaborate with physicists from Canada and the US and Denmark and Brazil and the United Kingdom, etc. So what is the LHC? It's the Large Hadron Collider. Hadron is probably a word that most of you aren't familiar with, but it's really just another name for a proton. So it's a proton collider. It's the world's most powerful collider. Some of you were probably following the fact that it turned on last September for about 2 weeks, and then almost immediately got turned off again by an accident, and it will start up again in August. It's 27 kilometers around, so that was that white line you could see on the picture of CERN. And it accelerates protons. The accelerator itself, as I said, is underground. Actually, I used to work at the accelerator, and I had to go to work and get in an elevator and go down 8 stories to get to the actual experiment. And what we do is we smash protons on protons, and as everything that in my field that we do is it's pure E equals mc squared. And I'll repeat that many times. You'll see it many times. We convert E, energy, into mass. And these pictures are just to show you, these are 2 of the experiments that are at the collider, and they're just to give you a sense of the size of these things. They're sort of beyond imagining, actually. You can see there's a person there at the one end of the Atlas experiment the experiment itself is kind of the size of this building. It's truly a monstrous thing. It takes data at a rate of something like 11,000 Encyclopedia Britannicas per second. It's pushing the envelope in all technical ways. And I'll hopefully try to explain to you why that is. What's an accelerator? An accelerator is really just something that takes charged particles and accelerates them. It adds energy to them because at the end of the day, it's energy that E is equal to mc squared. So we want as big of E we can get to get the biggest m. Okay. And what we have a tendency to do is we use electric fields to accelerate them, and then we use magnetic fields to bend them. High energy physics, which is what I do, is a global enterprise. It always has been. It's probably the most global enterprise there is. And it's being probed at accelerators around the world, and literally around the world, including the Triumph Lab in Vancouver, British Columbia. And of course, many universities. What we have a tendency to do here, my colleagues here, we make certain devices and then we have to take them to these labs. And we actually spend lots of time at these labs because that's where the action is. Okay, so before we talk about antimatter, I thought we should talk about matter, something that we all already know. And just to remind everybody, usually when one talks about matter, we're talking about atoms. And an atom is a nucleus of protons and neutrons with electrons circling around. Okay, so this shows what an atom looks like. And the sizes of these things, of course, it's called subatomic physics because the sizes are something unimaginable, really. That is 1/10 billionth of a meter is the size of an atom. The size of the nucleus is another 10,000 times smaller than that. And so it's a size that it's hard to imagine. But we do know atoms reasonably well. And of course, the simplest one is the hydrogen atom, which is just a proton with an electron going around it. And I show the hydrogen atom because, of course, we will talk about hydrogen because we will talk about antihydrogen, which is one of the things that I do research on. And the next simplest atom is helium, and that has 2 electrons, it has 2 protons and 2 neutrons. So 2 protons, 2 neutrons in the nucleus, and 2 electrons that are circling around. Now, that, of course, was the picture of the atom until about 1960. And now we know that that isn't correct, at least that isn't complete, that the atom is much more interesting than that. In particular, the protons and neutrons are much more interesting. They are not, in fact, they're little entities all by themselves, but they are sort of mini atoms themselves. But they're mini atoms made of these things called quarks. And the world is built up of quarks and electrons, basically. That's our world. And for a long time, we thought that was all there was to the world. So the fundamental entities in the world are quarks and these electron-like things called leptons. And I don't know, the people at the Department of Energy gave me this slide. I don't know if that means anything to you at all, but anyway, there's different types of them. And you know, the great thing about when you're a physicist and you discover a new thing, you have the right to give it a funny name, and so they give lots of funny names: strange quarks and top quarks and charm quarks, etc. The point being, though, that these are, as far as we know, the fundamental things that the world is made of. So here's how do we build a universe out of those things? Well, first we make nucleons, protons and neutrons, and they're made of quarks. So there's my proton and my neutron. And I put them together to make a nucleus. And then I grab an electron, and it goes around, and I make myself an atom. And then I just multiply that by billions and billions and billions and billions, and I end up with that. Okay? So the point is that as far as our understanding is, that is what the universe is made of. Okay? And that comes from many, many years of experimentation, et cetera. Now, one of the things I wanted to, and I'll very quickly allude to it because it's actually a very long and complicated subject, and that is that picture I showed with all these quarks and these leptons. We have a theory of how they interact, how they work together. That theory makes predictions that you can test, and those predictions and those tests agree to the 14th decimal point, and it's hard for me to emphasize how incredible that is. So our picture of the world, this so-called standard model, is the most precise understanding of the world that's ever happened. And we know that from measuring and comparing to these predictions. One problem is that all these particles in this theory have zero mass, and that's a little bit hard thing to understand as well. And so the God particle was this particle that was predicted by a man named Higgs, Peter Higgs, Scottish physicist, in the 60s, and others. And it was the way to get around this problem. Okay? Leon Lederman, who's won the Nobel Prize for Physics, who also missed his calling as a stand-up comedian, he wrote a book called The God Particle, which is about the Higgs particle. And ever since he wrote it, he's been unhappy with the fact that he used that, because now it gets used in movies, and people said the God particle, and then sort of religion versus science comes up, and it wasn't what he meant. But in any case, it is the last remaining peg in our understanding of matter, and we haven't seen it yet. And I was going to explain what it is, but I don't think I will. But what I will say is that it is the goal at the moment. It is the thing that we are all racing to find, because it is this, in some senses, as a scientist in particular, it would almost be better if we don't find it, because then the world opens up again and you think, there's things we don't understand. But at the moment, we are trying to find it. The LHC, the Large Hadron Collider, that's one of its primary goals, is to find the Higgs boson. There's also a collider called Fermilab outside of Chicago, which is just on the edge of possibly seeing it. And of course, they would love to see it first and scoop this Large Hadron Collider. And so this is a picture of the so-called Tevatron outside Chicago, which is a 1 kilometer radius collider. It's so much easier using metric units to describe that collider than when I go to the US. Of course, it's some number of miles around and some funny number. It is a anti-proton collider. So it in and itself, not only are we studying antimatter, we're using antimatter to study antimatter. Okay, antimatter. Let's talk about antimatter. It isn't fiction, although it's in a fiction book. We produce it all over the world. Enough of it, in fact, could destroy Rome. And the question is, what is it? So I want to approach it by again going back to E equals mc squared. There's an equal sign there. So it means that E is equal to mc squared. C is just, it's a speed of light, it's just a constant. So basically it's saying energy is equal to mass. That's what that equation says. And we see that all the time in our science. And on the right, you can see there's something we call a bubble chamber photo. And all that is that it's a detector in which a charged particle goes through and leaves a little trail of bubbles, and you can just photograph it. And so you literally have a photograph of the trail of a particle. And so you can see on that picture that you have some particles go this way and some particles go that way. And it turns out that this whole thing is in a magnetic field, and if you're a positively charged particle, you go that way, and if you're a negatively charged particle, you go that way. Okay? So we can tell what particles are negatively charged and which particles are positively charged. Now I want to concentrate and look a bit more closely at what's happening on the top left. Okay? You can see that if I'm coming in, I should have had a laser pointer, I'm sorry. If I'm coming in from the bottom right, there's nothing. There's nothing in this picture. And what does that tell you? If there's nothing in this picture, it tells you that it's something that was uncharged, had zero, doesn't have any electric charge. Well, that's light. That's a photon. That's the particle nature of light. So it's coming in, and it transforms into a particle and an antiparticle. In this case, it transforms into an electron, which in this magnetic field curls down to the bottom, and a positron, anti-electron, which curls up to the top. Okay? So there it is, right in front of your eyes, the creation of antimatter. And in fact, this is happening all the time in this room. It was predicted in 1928 by Paul Dirac, and people thought he was basically crazy. But it was predicted because it just came from that very picture that I showed before, that in his theory, you have energy creates, you can't have a zero charge thing create all of a sudden an electron. You have to have a positive charge created as well. And about 4 years later, it was observed. That picture there again shows the track of a charged particle, and if it was a negatively charged particle, it would be going the opposite way. So that's a positively charged particle. It's a positively charged particle that looks exactly like an electron, i.e. it's an anti-electron. So the world is actually composed of quarks, leptons, and antiquarks and antileptons. And that is our world, and the theory that we have that predicts it with extremely a precision that's unparalleled. So the question is then, can we make antimatter? As I said, we saw it created in that picture. As a matter of fact, it's happening all the time. This is a Geiger counter, which measures charged particles going through. So we have going through us all the time antimatter as we sit here, because particles are streaming in from outer space, hitting the upper atmosphere, and in that same process, they create particles and antiparticles. They create positrons and electrons. They create protons. They create antiprotons. And those come streaming down, and they're coming through us all the time. And we're okay. I mean, everybody's okay here. It also happens in radioactive elements. They create positrons. Certain elements that have so-called beta decay give off positrons, anti-electrons. And an example of something that gives off positrons is potassium, like in the banana. Okay? So every banana you have, I'll put these further away, I guess. Every banana you have has a certain amount of radioactivity to it. And so if I watch this banana, it's just streaming out. Positrons are streaming out of this banana. Okay, so I don't put this up there for you to be afraid of bananas, but more to try to, and you also have potassium-40 in your body. As a matter of fact, for most people, the most radiation they will suffer through in their whole life comes from their own body. There's absolutely nothing you can do about it. Okay, and as I said, it's part of evolution, and we seem to have survived it. Can we make antimatter? As I said, we do in accelerators all over the world, including SLAC, the accelerator at Stanford, Triumph, the accelerator in Vancouver, the LHC, Fermilab, et cetera, et cetera. So in the film, this antimatter is in this canister, which is filmed, and it's the big, it's a typical thriller thing where the clock is ticking down and there's only so many seconds left. It's suspended in this vacuum. And the question is, so why? Why go to all that trouble? I mean, why not just carry it on the plane and stick it in the Vatican anywhere? Well, I would argue that we already know why, and we just have to go back to that. If I looked at that picture, I said that I had a photon light coming in from the right, creating antimatter matter. I could equally, all the laws of physics are symmetric under time. In other words, they're the same whether you flip time backwards or forwards. I could equally look at that picture and say I have an electron and a positron come together and they annihilate into pure energy. Again, E equals mc squared. And so we would think, as I said, all of our laws of physics are symmetric. In other words, they're the same for the antimatter side as the matter side. Okay? So an anti-Tom Hanks would look very, I mean, actually, even this doesn't do it. He would look exactly the same, actually. Okay? I mean, you know, here they put different coloring to make him look sort of evil on the anti-side. But if Tom and his anti-Tom were to meet, that would not be good. And again, E equals mc squared. That's the key point. The point is I've converted, in this case, I've converted mass to energy. And our world is a constant fluctuation of going back and forth, energy to mass, mass to energy, energy to mass. Okay. Is this annihilation necessarily a bad thing? It's certainly a bad thing on the subatomic talk show here, where the Mu Meson show, where Matt and his long-lost brother Anti-Matt meet. And of course, you know, you don't want to be there the next second when they actually hug, because that's the end of the show. But in fact, we use matter-antimatter annihilation in medical imaging. If I take something that has, say, for example, potassium-40, and I put it in the blood, and I put it in the brain, for example, what's going to happen? Well, it's going to emit this positron, and the positron is going to very quickly, because since we're basically made up of electrons and protons, it's going to very quickly find an electron, and it's going to annihilate. So this is the basic process. Okay? It's going to annihilate to 2 gamma rays. These 2 photons, these 2 light rays we call gamma rays. Okay? So that's E equals mc squared. So that's the basic idea of a PET scanner. I don't know if anybody's had a PET scan, but you know, I'm sure how many people are aware of the fact that P in PET stands for positron, as an anti-electron. Okay? So we're using antimatter to do medical imaging. And here's the idea. You, as I said, you put some radioactive source in a person's brain. Usually you inject it and so they have it in the blood. And then it annihilates, giving off these photons, and we have these gamma ray detectors that we just detect all these photons, and we image that part of the brain where this is happening. Okay? So the idea being that, you know, antimatter is not necessarily a bad thing. And even more important, it's from the years of study of it to understand it that allows for something like a PET scan. Okay? To go back to Angels and Demons, in the movie, they had a 1/4 gram of antimatter. Now, that doesn't sound like a whole lot. A 1/4 gram is the equivalent of 11 grains of rice, and I got this 11 grains of rice from my colleague from Berkeley, and I just actually today counted them. There's actually 10 there. So, okay, 11 or 10 grains of rice is about a 1/4 gram of matter. Okay, so if you had 11 antigrains, when you do the calculation of what E that is, it is equivalent of something on the order of 5 to 10 kilotons. So it is equivalent to a nuclear explosion. Okay? So, I mean, that science is actually correct in the movie, in the sense of that amount of antimatter really is a problem. And again, I got this from my colleague from, I just thought it was kind of a neat movie. This is St. Peter's Square in the Vatican, and we're zooming out, and then kaboom, the explosion happens, and that's how much the area of Rome and the Vatican City would be destroyed by that. Okay? So, you know, if it was possible, it'd be a serious thing. And luckily for us, it's not possible. Even at Fermilab, which is a proton-antiproton collider, the amount of antiprotons we make is 2 nanograms, 2 billionths of a gram a year. And that's using a lot of energy to make those 2 billionths of a gram. Okay? So to make my 1/4 gram bomb, which is the equivalent of a nuclear bomb, would take 100 million years. Okay? So it's really something, you know, if you're gonna, if your takeaway message is don't be afraid of an antimatter bomb. Okay? Unfortunately, it's also really probably not useful for an energy source. It's a beautifully clean energy source if you could have it, but unfortunately, it's just not in the books to use it. And the reason being is it takes far more energy to make the sample of antimatter than you'll ever get out of it. Okay, fine. Also in Angels and Demons, they have it suspended in this. What does she say? She goes in an electromagnetic trap or whatever she says. It's in a bottle, and of course the main thing is we have to make sure that it doesn't hit the walls of the bottle because, as we've just discussed, it'll annihilate. Okay. So that is what we are doing. Myself and, as I said, a bunch of collaborators from across Canada and across the US and Brazil and the United States and the UK are trying to make anti-hydrogen, an anti-proton and an anti-electron, and make the equivalent of hydrogen but the anti-version. But we can't just make it and say, oh, you know, hallelujah. We have to make sure that we trap it in a bottle, because otherwise if it hits the walls, it'll just annihilate. And of course, we can't do much with it. So we have been doing this for almost a decade. We've made about 100 million of them so far. You know, it sounds like a big number, but if you compare that to the number of atoms in your body, it's really minuscule. And if we could get them all together and just annihilate them, then we could light a laser pointer for about a second. Okay? So, and if you took all of the antimatter that's been created so far by man-made machines, you could annihilate it on your finger, and it'd be equivalent of maybe lighting a match on your finger. Okay? So at the moment, it's really not a problem. This was a picture of our group meeting last year in Vancouver, and you can see me hiding in the back there. So I just want to give you some feeling for, in the movie, the trap looks, the bottle looks like it's about this big, and that turns out to be actually pretty much close to what it really is. This is, on the picture there is my collaborators, Makoto is from Triumph in Vancouver, and Richard is a student in Calgary. Then there's Carlos, a Brazilian, and there's an American colleague, what's his name again? Ben. And that shows the size of the trap. He's holding on to it there. On the right is just a picture of showing what the trap is, and what we do is we bring in antiprotons that we get from Cern. We do this at Cern because there's only two places in the world we can actually get antiprotons, Cern and Fermilab. And then we get positrons, anti-electrons from a sodium iodine, a sodium source, which is radioactive. Then we bring them together and try and make, what we do is we make clouds of anti-electrons and clouds of antiprotons, and then we try and coax them together to try and make atoms. And it's actually an incredibly difficult thing to do. I thought it was going to be simple, and it's not at all. Now, Dirac was an amazing character. He won the Nobel Prize for Physics in 1933. Remember, he was the one that predicted the existence of antimatter. And he says that if we accept the view of complete symmetry between positive and negative electric charges, we must regard it as rather an accident that the Earth, actually the universe, contains a preponderance of negative electrons and positive protons. It's quite possible for some of the stars the other way around, that some of the stars could be made of negative protons and positive electrons. As a matter of fact, when we look at that picture again, that may all be antimatter for all we know. Because in fact, it will look exactly the same in terms of the light that it gives off. Because light itself, as we saw, light produced electron, positron. It didn't really care whether it was an electron or a positron. And so anti-atoms, anti-stars, anti-galaxies, anti-galaxies, whatever, would look exactly the same as far as we could tell. And that brings us to the moment of creation, which of course is the Big Bang. And that's another mystery for physicists that most people probably don't think is a mystery at all. And that is, just as we saw that a photon produced an electron and a positron, the Big Bang was neutral in everything. And so the Big Bang produced just as many positrons as it did electrons. It produced just as many protons as it did antiprotons. It produced just as many particles as antiparticles. And you might just say, well, okay, obviously the Big Bang was wrong. I mean, you look around the world and you don't see any antimatter, so obviously the Big Bang picture is wrong. But in fact, the Big Bang picture predicts quite a number of things which we observe. So we believe it's right. And so one of the big questions in science is what happened to all that antimatter? I mean, it's not like you could just take an exit door out of the universe. I mean, where'd it go? As I said, 14 billion years ago, we start off with equal amounts. And then at some point, there was just a little bit more matter than antimatter. As a matter of fact, for every 10 billion antimatter particles, there was 10 billion in one particle. And so the 10 billion and the 10 billion annihilated, leaving one. And the reason that we know that fact, actually, is because if you look at the number of particles in the universe compared to the number of light particles, there's 10 billion times as many light particles. Okay? And they come from annihilation. So that's not just, like that number isn't just picked out of a hat. It's an experimental, measured number. So that's one of the great challenges of physics. And the question is that we know that the answer lies in some very subtle difference between matter and antimatter. And the reason we're doing anti-hydrogen research is because the most precisely measured system in science is hydrogen. It's the simplest, and we can predict it incredibly precisely. And so if we can make measurements on antihydrogen the same way we make on hydrogen and compare them, then we can see if there's some little slight difference. And so that's the idea. And the idea is to zap them with lasers, and then they emit light, and we measure that light very precisely, and we just see, is the light coming from antihydrogen slightly different than light coming from hydrogen? Okay. We know it's not a lot different. We know that right now. That's the idea. Another kind of interesting, funky idea is we don't really know a lot about gravity with respect to antimatter. I mean, for example, we know perfectly well that the apple will fall to the earth, and we're pretty sure that the anti-apple will fall to the anti-earth exactly the same way. What we actually don't know, though, is whether an anti-apple will fall to the earth, whether an anti-apple will be repelled by the earth. That's actually an experimental question, and we don't know the answer. And it's actually an extremely difficult measurement to make, and that's because gravity is such a weak force. But that's another experiment we're going to try and do. There's a lot of fun you can have with antimatter. Let me just quickly go through a couple of other big questions that we're looking at. One is that it was a bit of a shock in the last about 5 years to discover that most of the universe is actually not made of matter. It's made of this stuff that's given very sort of spooky names of dark matter and dark energy. And we don't know anything about either one of those. And so it's kind of a spooky thing that 95% of the universe is made of stuff that we have no idea what it is. But as an experimental physicist, that's the challenge. Can we find out what it is? Dark matter is called dark because it doesn't give off light. It's kind of like a black hole. But we know it's there. We actually know a fair bit about it in some senses, except exactly what is it? We don't know. And we're searching for it, as usual, on Earth, in experiments on satellites. I just put up here SNOLAB, which is the Sudbury Neutrino Observatory. They've expanded to now have a number of experiments there, and some of them are looking for dark matter. We'd like to make dark matter, and the collider, the LHC, is the perfect place to make it, actually. Dark energy is even weirder. Haven't a clue. In some sense, we don't even know where to start. And just to finish off, just the people here at the university that are doing research on antimatter includes my colleague Wendy Taylor, who works on ATLAS, the experiment at the LHC, Eric Hessels and Cody Story, who work on ATRAP, which is an anti-hydrogen trapping experiment. Myself, I work on ALPHA, which is an anti-hydrogen trapping experiment. And then we also have a bunch of theorists who, try and tell us what's really going to happen. If you want more information, there is a number of places that you can look to get more information, or else you can just ask me right now. Thank you.